Well, it's my pleasure to introduce Professor Bob Hoffman-Lantek from the University of Wisconsin, who is one of the leading experts on the interface of neutrino physics and astrophysics, and nuclear astrophysics in particular. So he's going to tell us about something relevant.
Well, thank you, George. I am very happy to be here, seeing a lot of interested faces. I understand there is another group on the beach today, but I'm going to actually cover both, well, not just two, but particle physics, nuclear physics, and astrophysics, just to show you that astrophysics was an interdisciplinary subject before interdisciplinary subjects became keywords. I'm going to tell you a number of things about neutrinos, but I will start at the beginning, and I will tell you some things you already know. That's okay. So, neutrinos are fascinating particles. Why? They are the only neutral fermions we know. Well, let's start discussing what they are. I'm going to start at the very beginning. What's a neutrino? And I'm going to discuss what a particle is. And then why the neutrinos are fascinating will come after that. Well, the next thing I'm going to tell you is probably stuff you already know. But Vicky Weisskopf once told me, never underestimate the pleasure people will get from listening to things they already know. So it's always good to tell you that you already know quite a few things. And this is kind of a history of science. And there will be a lot of historical comments as I go on. Well, neutrinos came out of a puzzle about the radioactive decay in the early 1920s. What happened was that they were observing the radioactive decay from a mother nucleus into a daughter nucleus, and of course, electron was being emitted. And then, as now, they could only detect charged particles. So they detected the electron. But the energy momentum conservation from what they had seen told them the data should look like this. There should be a fixed electron energy, whereas it looked like that. Now, this was a problem. And famous Niels Bohr, the famous Niels Bohr, said that perhaps energy momentum conservation no longer holds at the microscopic level. Well, if you give up energy momentum conservation for a two-body decay, this is a perfect thing. Whereas Wolfgang Pauli said that in this reaction, there is a third particle produced that you cannot yet see. And that third particle takes out extra momentum and extra energy, and you get the distribution like that. And that extra particle is the mighty neutrino. Of course, he did not call it neutrino, Pauli. He called it neutron. You probably don't realize Pauli was an incredibly prejudiced man. And he actually didn't like to talking to students. He kept his office hours in a very expensive pastry shop. So the students have to actually save money so that they can go to the pastry shop to talk to him. And he was very opinionated about everything. So he was a very big guy, very fat. And so he called this particle actually neutron. Later, Fermi called it neutrino. It was an inside joke because neutrino means the little neutral one, and Pauli was neither little nor neutral. Well, but of course, Pauli was asked to come to a talk just before Christmas of 1930 to a conference to give a talk about his proposal, a conference in Tübingen. He lived in Zurich. If you look at the map, Tübingen and Zurich are not too far away from each other. He did not go. Instead, he sent this very famous letter, which starts, "Dear radioactive ladies and gentlemen." He did not go. Instead, he sent a letter. And in the letter, he said, well, he really cannot come to the conference because he has to attend a party. He's the only physicist I know who turned down a conference invitation to go to a party. But nevertheless, the real reason was that he was afraid to stand in front of a bunch of physicists and tell them that he's proposing a particle that can never be detected. Boy, how much the times have changed. Now, physicists propose particles all the time that don't exist, can't be detected, and we're not really worried about it. But Pauli was worried about it, and he sent that message. Basically, he says he proposes a new particle, and you can actually read the letter. So neutrinos are actually quite interesting, and if you look at the timeline of the neutrino physics, there are a lot of eccentric characters. I mean, Pauli is one. Fermi wasn't perhaps as eccentric as Pauli, but as you know, he was eccentric in the sense that he's the last physicist I know who was a theorist and experimentalist at the same time. He made major contributions to both theoretical and experimental physics, and that was before computers. And if the computers existed, I'm sure he would have done computational physics as well. And then, of course, Majorana, who was quite an interesting character. As you know, he disappeared. He literally disappeared. Pontecorvo, actually, then he was a communist, left for Russia, for Soviet Union afterwards. And of course, finally, Maria Mayer, the famous San Francisco housewife who got the Nobel Prize. San Diego, housewife who got the Nobel Prize. So you see, she actually is the person who proposed the double beta decay.
Well, you have to understand, that was the description of
Yes.
San Diego Union Tribune.
Exactly. No, I was going to say that. So she's the one who actually proposed the double beta decay. And she moved to San Diego at some point. She had an appointment, some sort of an appointment at the university, but not a real faculty position, I think.
No, that was in Chicago.
It's Chicago.
UCSD gave her first real job.
Okay, I stand corrected. So, but nevertheless, she got her Nobel Prize when she was in San Diego. Then she must have retired. She must have been retired at the time of getting the Nobel Prize. Why does the newspaper call them housewife then?
Because they couldn't think of what else to call it. Right? It's inconceivable that you was a professor.
Isn't that amazing? Again, times have changed.
The Union Tribune headline, and the physics department has this, you can look at it. San Diego housewife gets Nobel Prize.
I actually looked for that article to show you guys with that headline. I couldn't find it on the web, but maybe next time I'll do that. Okay, so what I'm going to do today is, well, we have seen some of these things, why neutrinos oscillate, why they play an important role in astrophysics and cosmology, and what they have to do with the element production. We had seen quite a few of that already in this series of lectures. Now, the next question, which is actually a very deep question, and a question in which neutrinos play a very important role, is what is a particle? We say neutrinos are particles. What is a particle? Well, I will tell you that the best answer will follow from symmetry arguments. Now, symmetry is an incredibly important concept, incredibly important tool in physics. It helps you with everything, really everything. It helps you with computations also, because if you know the symmetry of your equations, you can check your numerics quite well. So symmetry is a very incredible tool. And the answer, the very first answer to this question of what a particle is, was given by Eugene Wigner. He said, a particle is an irreducible representation of the Poincare group. Now I have to translate that. Right? What does that mean? Well, it's actually quite an interesting thing. Well, first of all, let me remind you the Lorentz transformations, Lorentz boosts. Let me remind you what is left invariant under Lorentz transformations. The very first one is proper time. I'm not writing C's. C is equal to 1. The very first one is the proper time. The next one is the mass, because E squared minus P squared is a Lorentz invariant, just like T squared minus R squared. Well, another one, if you take electric and magnetic fields, is E squared minus B squared. Another one is E dot B. So these are the Lorentz invariants that we had known by the time of neutrino, proposal of neutrino. But if you look carefully, there is mass showing up there. So mass has something to do with the Lorentz transformations. It is the quantity that is left invariant under the fundamental transformations of nature. Well, it turns out there are a few other fundamental transformations. One of them is rotations. We assume that the space is invariant under rotations. And another one is translations. And as you know, the conserved quantity for the invariance under translations is the momentum. Invariance under rotations is the angular momentum. So those are the conserved quantities. And the Poincare group is the group that includes Lorentz boosts, translations, and rotations. And that's why Wigner said a particle is an irreducible representation of the Poincare group. So a particle has to have mass. The mass can be 0, but it has to have mass. And that brings us to the question of neutrinos. Neutrinos, we were told already, have different masses, different mass eigenstates. Well, so this is a very deep question. And let's start exploring the question of mass next. What is mass? Well, this is again from what you know from field theory. You typically can write down the mass term in the Lagrangian for the Dirac equation in this form, m psi bar psi. Well, typically you can introduce the left and the right-handed components of it, and then this term takes this particular form. It is a term which connects the left and the right-handed components, like the famous Escher painting. So a mass is nothing but the coefficient of the term in the Lagrangian, whether it's fundamental Lagrangian or a composite Lagrangian, non-fundamental effective Lagrangian. We'll talk about effective Lagrangians as well. It's the term that connects left and right-handed components. Mass is the shaking of two hands, left and right-handed components. That's what mass is. And in the standard model, all elementary masses, possibly except neutrino masses, are generated by Yukawa couplings of the Higgs. By elementary masses, I mean the masses of electrons and masses of quarks. We do not know about masses of neutrinos, and we do not know what the dark matter is, so we cannot tell you what this mass comes from. And there's, of course, dark energy. You heard a lot that Higgs is responsible for the mass of the universe. It's only responsible for the masses, as far as we know for sure, of electrons and quarks. We don't know about neutrinos. Maybe it is. And as you know, Higgs has very little to do with other masses. For example, masses of protons, neutrons, etc., are generated dynamically by the QCD interactions. So for example, in the early universe, we use that, the masses being not fundamental quantities. Okay, so let's start thinking about what mass of a fermion is. And for that, I'm going to use the chiral representation of the Dirac matrices. It's the most convenient for what I want to do. So in the chiral representation, gamma 0, or in the old notation called beta, is given by this. Alpha is given by this. Alpha is gamma 0 times gamma vector, and gamma 5 is given by this. And you can see why this is convenient, because mass connects left and right-handed components. So it connects the term that comes with 1 minus gamma 5 with the term that comes with 1 plus gamma 5. And you see that this term, this particular representation of the Dirac matrices actually separates those two components quite nicely. So I'm going to introduce then two concepts. One is the chirality. Chirality is basically gamma 5. And the other one is helicity. Here, K is the momentum of the particle. So, and sigma is the spin, total spin. So sigma dot k divided by the absolute value of k. In other words, helicity is the projection of the unit vector along the direction of the momentum on the spin. Well, you can easily show, I mean, using these, this capital sigma, capital Greek letter sigma, is basically a sigma here. It's a 4 by 4 matrix, sigma here, another plus sigma here, as opposed to alpha. So you can easily show that chirality and helicity commute with one another. I mean, it's an exercise to you. I'm sure you have done this if you are taking classes in field theory. You can also easily show that gamma 5 square is identity, square of the helicity is identity, so eigenvalues are plus and minus 1. So since they commute with each other, you know from elementary quantum mechanics that they can be simultaneously diagonalized. So let me call their simultaneous eigenstates lambda chi. Lambda is the chirality eigenstate of gamma 5, and chi is the helicity eigenstate. I could have changed the notation. So sigma and chi take only values plus minus 1. Now, the reason I introduced this, this shows you something very interesting once you put into Dirac equation. It's, I think maybe George may mention this in the lecture tomorrow, a quantum kinetic derivation of the neutrino propagation, and you will see this again there. So these operators, of course, act on the fermion fields. Fermion field, you can either write it in the position space or in the momentum space. Well, in the momentum space, I will use the momentum space because in the momentum space, these are the creation annihilation operators for a neutrino with momentum k. So that's a nice way of looking at it when you go to many body description of neutrino gases in the supernova. So I'm going to use the momentum space description, but of course the position space is just as good. Here S is the Dirac index. As you know, it's the dimensionality of these matrices. It goes from 1 to 4. Now, let me now then project this fermion operator in the momentum space, that is to say creation operator, onto the helicity chirality states. Let me call the projection onto the state where helicity and chirality are the same to be B dagger, and the state where helicity and chirality are different to be D. And if I do that, and if I write down the free massless particle Hamiltonian and insert these definitions all together, then you'll see that the free massless particle Hamiltonian can be written in this way. Now, the reason I actually use B and D, I'm an old guy. I learned field theory from Bjorken and Drell, and there the creation annihilation operators for fermions are indicated by B and D, but you can use anything else you want. Of course, here there's a minus sign, but notice that the order is DD dagger. Since the fermions anti-commute, if you write them in the normal ordered way, there's a plus sign there. So if particles were massless, and as you know now that these will be the particles, these will be antiparticles, and they would each carry energy k. So this is simply energy, total energy of the free massless fermion system, number operator for particles, and number operator for the antiparticles, and they would both carry momentum k. Now, as soon as you introduce a Dirac mass term of this form, you can just put everything in and see then the Dirac mass term is equivalent to this expression in terms of the creation annihilation operators. Now this looks quite interesting, and if I write this down again, this is the total Hamiltonian. I'm not going to write the arguments anymore. This kind of an Hamiltonian is encountered a lot in many body physics. It's a quadratic Hamiltonian in creation annihilation operators, and it can be diagonalized by a unitary transformation, typically called Bogolubov transformation. And this is the unitary transformation, and here is the mixing angle of those two. You can actually show that you can diagonalize this Hamiltonian in such a transformation. This is var phi. And you can rewrite after that transformation the Hamiltonian in this form, which is the Hamiltonian for massive particles. This is the number of particles plus the number of antiparticles, if you wish, and the energy is k squared plus mv squared. The more important thing you should notice is that the mixing angles are given by k over energy, and cosine of the twice the mixing angle is k over energy. Sine of twice mixing angle is mass over the energy. For neutrinos, in the past, we typically ignore this term because neutrino masses are very small. The neutrino energies that we deal with in the experiments typically are order of MeV or higher, whereas the neutrino masses are fraction of EV, so we ignore that. But it can be very important in the supernova context. And I think, have you heard anything about that yet, George? No. And maybe you'll mention it tomorrow a little bit?
Vincenzo.
Okay, Vincenzo will. Okay. So we will hear the importance of these terms. But the point here is that there is always a, if you wish, wrong-handed component.
What Vincenzo and perhaps I will talk about actually doesn't mention this very nice underpinning of what's going on.
Okay, I see.
Given the mass.
All right. Okay. All right, so, well, of course, you see that there is always, if you wish, a wrong-handed component mixing. So if this is a really Dirac neutrino, this extra component will be a sterile one. And this would be the mixing between active and sterile components. If you make a model, you can actually calculate that. Of course, you have to make a model of some interaction in order to do that. So now there is actually one other way you can get mass, and that was discovered by Majorana, Ettore Majorana. Majorana was a student of Fermi, and he said, wait a minute, you may not need a, if you start with a left-handed fermion, you may not need a right-handed fermion. Mass is basically the connection between left and right. But if you start with a left-handed fermion and calculate its charge conjugate, the charge conjugate of the left-handed fermion is a right-handed object. So then the product of those two again connects right and left hands. So it's a proper mass. So he said, well, why not? This can be a mass as well. Well, you can actually, then he called this the Majorana mass. I use M sub capital M to indicate that this is a different kind of mass, but nevertheless, it is a mass. So this is what Majorana proposed as a mass term. Of course, there are two possible Majorana type mass terms. You can either start with a left-handed fermion and take the charge conjugate to make it right-handed and connect them to get a mass, or you can start with a right-handed fermion, take its charge conjugate, makes it left-handed, and you get a different mass. There's absolutely no reason why those two masses have to be the same. You have to make models to calculate whether they are the same or not. So there are actually, if you wish, for a single fermion field, there are really three possible mass terms you can write. One Dirac mass term and two Majorana mass terms for a single fermion field. And that's, of course, very important. And we shall see why it's important. Okay, the next thing I just want to briefly mention is that we now know that neutrinos mix. So the interaction eigenstates are not the same as mass eigenstates. There's a unitary matrix that mixes them. Now, one should point out that if the neutrino mass were 0, this mixing would be irrelevant because it would be simply a change of basis of the standard model. In the standard model, this is a typical interaction between electron W and electron neutrino. Instead of the interaction vertex strength being G, it would be simply G times mu E sub I, and you would have the ith mass eigenstate. But if the mass were 0, it wouldn't matter. This would be simply renormalizing the interaction strength. So it's only important when the mass is non-zero. And here is the standard model interaction of the neutrinos in full glory with W's and Z's. In the standard model, only the left-handed objects interact, only left-handed particles interact, only right-handed antiparticles interact. Okay, now I told you that the symmetries are very important. And of course, standard model has its own symmetry. And that is the SU2 weak symmetry. And let's look at this a little bit more carefully. The symmetry is not just SU2 weak, but there is a U1 left over from the symmetry breaking in the standard model. So the symmetry of the standard model is SU2 weak times U1. Now, in the standard model, the left-handed and right-handed neutrinos are treated very differently. And that's actually an important thing. That's why you sometimes hear that the neutrino mass is not permitted in the standard model. What happens is that the left-handed neutrino sits in a weak isospin doublet together with the left-handed component of the associated charged lepton, whereas the right-handed neutrino is a weak isospin singlet in the standard model. Now, this actually is not so difficult because you are all familiar with angular momentum from quantum mechanics classes. It's just like angular momentum, like spin. So typically, these are the doublets. Here is a weak isospin 1/2 doublet. So there is a neutrino, a left-handed neutrino in the upper part, and for example, electron neutrino, and left-handed electron in the lower part. That means the third component of the weak isospin for neutrino is plus 1/2. The third component of the weak isospin for electron is minus 1/2. And the right-handed objects, both right-handed neutrino and right-handed lepton, are weak isospin singlets. So the weak isospin for them is 0. So these are 1/2, and these are 0. And Higgs field, after the symmetry breaking, also sits in a weak isospin doublet, and its third component is minus 1/2 after the symmetry breaking. So this is all you really need to know about the standard model in order to follow what I'm going to tell you next. Okay? Now, let's think about the mass term. A mass term connects left and the right-handed components. So for example, the Dirac mass term is given by this. But such a neutrino mass term may break the weak isospin symmetry. One can think it is not permitted in the standard model. However, that is not true. Do you know the answer why it's not true? From quantum mechanics classes, you had studied spin properties. Because the complex conjugate of a spinor transforms in exactly the same way under SU2 as the original spinor. So you can put in the complex conjugate and write down a particular object, but it's not nice. Well, so you still need a right-handed neutrino component to do that. And it's not there in the standard model. So however, you can actually have Majorana neutrino mass in the standard model, since the Majorana neutrino is always left-handed. But in order to see how you can do that, now next I have to tell you a few things about effective theories. Again, I'm only going to tell you enough to follow what I'm going to say. So here is a brief introduction to effective field theories. Okay, now Lagrangian is what's Lagrangian? It's kinetic energy minus potential energy. So it has dimensions of energy or mass. Energy and mass are the same, right? So, but typically in field theory, we deal with Lagrangian density. We take the Lagrangian density, integrate it over the volume to get the Lagrangian. So then Lagrangian density has dimensions of energy divided by volume, or has a dimension that goes like mass to the power 4. Okay, so that's the dimension of Lagrangian density. So for example, if you define the dimension, scaling dimension of x to be -1, the momentum will be +1. And then because obviously scaling dimension of Planck constant is 0. So clearly, the scaling dimension of a Lagrangian has to be 4. This should be true for any Lagrangian density that you can write down. Otherwise, it's not a proper Lagrangian because it does not describe energy. Okay, now let's consider the mass term for fermions. It goes like mass times psi bar psi. Well, we know that the mass term in the Lagrangian density. We know that this term should go like mass to the power 4. But there's a mass in the front, so then the scaling dimension of psi bar psi should be 3. That means that psi should have a scaling dimension of 3/2. In other words, it is a dimensionality. It is mass times mass to the power 3/2, if you wish. So scaling dimension of the fermions is 3/2. In the standard model, once after after the spontaneous symmetry breaking, Higgs give you the mass, so then the scaling dimension of Higgs should be 1. Okay? So these are the scaling dimensions. And what you're trying to do, to write down a Lagrangian which has scaling dimension 4. Okay? Now, I'll give you an example. You can actually, in effective field theory, you only use that information plus the symmetry principles to write down the Lagrangian that you can write down. Okay, so here is an example. Let's consider the QED Lagrangian. What is the Lagrangian density for QED? It is 1/2 E squared minus B squared. Well, what are the symmetries that we would like to impose on QED? One of them is the Lorentz invariance. And we just had seen that E squared minus B squared is a Lorentz invariant quantity, right? Well, another Lorentz invariant quantity is E dot B. Why do you think E dot B is not in this Lagrangian density for QED? What's wrong with it? It is not there. Clearly, it must break a symmetry that we would like to impose on QED. What symmetry does it break? No, you can make it consistent. Not gauge invariance. It breaks another fundamental symmetry. A discrete symmetry. Actually, not quite, but time reversal. You know, if you just think about this, under time reversal, B changes direction, so E dot B changes direction. So it violates time reversal invariance. So you really cannot have that. So this is the only term that you can have. So then, of course, you're now interested in corrections to QED that comes from physics at energies that you cannot probe. These will be, of course, higher order in the fields. So the corrections can be, for example, E squared minus B squared squared, because that is consistent with Lorentz invariance, and that's still consistent with the time reversal invariance, for example. And here, under time reversal, E goes to E, but B goes to minus B. So that's why we pick E squared minus B squared. So then we need to add terms that are consistent with the symmetries of the theory, but Lorentz invariance and time reversal invariance. So what are those terms? E squared minus B squared squared is consistent with both symmetries, so we can add that. E dot B squared is consistent with those symmetries, both time reversal and Lorentz invariance, so we can add that. But E dot B times E squared minus B squared, while it's consistent with Lorentz invariance, is not consistent with time reversal invariance. So you cannot add that. So then we know that those two terms have to be there. Well, then we need to write down what's in the front. Well, what is the dimension of mass dimension of E squared minus B squared? what? 4, right? Because it's Lagrangian already. So this term has mass dimension 8. So does this term. They have both mass dimension 8. But we want the Lagrangian to have overall mass dimension 4. So we need to divide that with some energy to the power 4. So that this quantity is then still a Lagrangian of mass dimension 4. So in general, if we didn't know any physics, then we would write alpha, well, sorry, I shouldn't call alpha, beta times e squared minus b squared squared plus gamma times e dot b squared divided by lambda to the power 4. And that would be end of it. And alpha and beta and gamma you have to get from experiments in a phenomenological way. But we know what the physics is. What is the physics? Charged particles. Physics at higher energies is charged particles. So clearly, all you need, since you're dividing by lambda to the power 4, all you need for lambda is the lowest energy, because that's the highest contribution. Well, what is the lowest energy that corresponds to the missing physics here? The mass of the lowest charged particle, which is an electron. So that's why you have me to the power 4. And of course, the electron interaction is alpha squared. You can put that in. So you can actually get alpha squared divided by me to the power 4, and this term and that term from effective field theory without doing any further work. In order to calculate this numerical constant, 2 over 45 here and 14 over 45 there, you actually have to do a calculation. But you see, effective field theory gives you everything up to numerical constants. Okay, that's a very brief introduction to the effective field theory. Now let's apply it to the neutrino mass. Well, here is the neutrino mass term I can write down using effective field theory and only the standard model fields. What's the neutrino mass? Well, neutrino mass is connecting left and right-handed components. In the standard model, I do not have a right-handed neutrino, so I start with the left-handed neutrino. I start with the left-handed neutrino, and I write down its charge conjugate. So this is a perfectly fine interaction that is permitted by the standard model fields. But remember, the symmetries have to be preserved. What is the third component of the weak isospin for neutrino? It was plus 1/2. So this term that you can write down has a third component of weak isospin plus 1. That's not good. It's not invariant under weak isospin. It has to have weak isospin 0. So I need to introduce some other stuff that has weak isospin minus 1. Well, the only thing I can introduce is Higgs. Higgs has weak isospin minus 1/2. So this has weak isospin minus 1/2, another weak isospin minus 1/2. So weak isospin minus 1, weak isospin plus 1. So this whole thing will have weak isospin 0. Hence, it is permitted by the symmetries of the standard model. However, let's look at the mass dimensions. This has mass dimension 3/2. It's a fermion. 3/2, 1, 1. So total mass dimension here is 5. But for it to be a proper Lagrangian, it has to have a mass dimension 4. So you need to divide it by some energy scale. And then this is an effective Lagrangian. And of course, there is a numerical coefficient that you have to get from the data. This is an effective Lagrangian that describes neutrino mass. The amazing thing here is that this is the only dimension 5 effective Lagrangian you can write down in the standard model. There is no other Lagrangian you can write which has mass dimension 5. So of course, you can write down mass dimension 6 Lagrangians, but mass dimension 6 Lagrangians have to have a square of the energy scale. So they're suppressed. In other words, the largest contribution of new physics to the standard model is nothing but the neutrino mass. And there is no other contribution which is really comparable to the neutrino mass. This was noticed by Weinberg in the 60s, but it was not really appreciated until now. So this is, of course, this term is not renormalizable. But that's not an issue, since it's an effective Lagrangian. Of course, there are other ways you can do that. If you introduce Higgses which are not in the standard model, you can write all sorts of other neutrino masses. Here's one example, but it really doesn't matter. So this is the physics beyond the standard model that you can write down by the local operators representing standard model fields. The dimension 5 operator is unique, and it gives you neutrino Majorana mass. There are dimension 6 operators, and dimension 7 operators include the Majorana neutrino magnetic moment. And I don't know if we have time to talk about that, but the neutrino magnetic moment is suppressed by 2 orders of energy scale from the mass. Okay, so this is the Majorana mass term. As I said, neutrino mass terms are not included in the fundamental Lagrangian of the standard model. To introduce a Dirac mass term for the neutrino, you have to introduce a right-handed neutrino field to the standard model. It's not a big deal, perhaps, but it's an additional field you're introducing. Or if you want to write down a neutrino mass using the standard model fields, you can write down a Majorana neutrino mass, but it is dimension 5. Whereas the Dirac neutrino mass would be dimension 4, but you're introducing a new field which is not in the standard model. So this is an interesting aspect of this. So how am I doing in time?
You can end wherever it's convenient. I mean, this is the coffee break time. We want to start with Evan Kirby about 11:30, so it's up to you, Bob.
Okay, well, let me start saying a few words about solar neutrinos, and then I'll stop. So I'll now switch gears and talk about the first subject. The original subject of this lecture is the solar neutrinos. And of course, here you see the characters associated with the solar neutrino physics, and we'll come to that. Solar neutrinos can come, well, actually stellar neutrinos, I should really say. Stellar neutrinos can come from a bunch of reactions in the sun. These are all the neutrino-producing reactions in the sun. And this series is called the PP cycle, and this series is called CN cycle. And in the sun itself, the PP cycle is the dominant one. And these are the nuclear reactions in the sun. So you actually can go through all these nuclear reactions, and a number of places you actually emit neutrinos. So there are a number of possibilities, but most of the neutrinos come from the fusion of PP. And there are some neutrinos where the PP are fused with an electron as well. This is a very small branch. And then later, following the nuclear reactions, there are some neutrinos that come from electron capture on beryllium-7, and then, or beryllium-7 can capture a proton, become boron-8. Boron-8 can decay into beryllium-8, which eventually decays into 2 alpha particles, and a neutrino comes out. Now, I don't know if this was discussed before, but let me just show you this, and I'll stop after a few transparencies. This is how you calculate reaction rates in astrophysical environments. You basically have to take the cross-section. In order to get to the rate from the cross-section, you basically have to integrate over the distribution of energies. And this is how it's done. Typically, you take a Maxwell-Boltzmann type distribution. You have to be careful, because when you deal with photon reactions, photons don't follow a Maxwell-Boltzmann distributions. They differ from Maxwell-Boltzmann because they follow Bose-Einstein, and that can cause problems in the reaction rates. But nevertheless, you calculate reaction rates in this particular way. Now, many times people discussed reaction networks. And let me give you an example of a reaction network in the sun. And after that, I will stop. So here are this is the reaction network. These are all the possible reactions. And typically in the sun, you have hydrogen, deuterium, helium-3, helium-4, beryllium-7, and lithium-7. These are what you produce. No free neutrons, for example. So then you write down a differential equation that describes the change of the hydrogen concentration in the sun. And of course, you know you can get rid of hydrogen by having 2 protons fuse. So then the rate for that reaction, total rate, will be, of course, the concentrations of the protons squared, since there are 2 of them. You have to divide it by 2, since double counting. And then you multiply the whole thing by the rate of that reaction that you calculate the way I talked about. And of course, there's a factor of 2 in the front, since there are 2 possibilities. And since this reaction is eliminating hydrogen, there is a minus in here. It is decreasing this ratio. Similarly, the hydrogen-deuterium fusion is also decreasing hydrogen. So there's a minus there times the rate of that. And the fusion of 2 helium-3 is again increasing hydrogen because it produces hydrogen. Proton capture on beryllium-7 decreases hydrogen. Proton capture on the lithium-7 decreases hydrogen. So this is the differential equation that describes the change of the hydrogen concentration. Deuterium is much easier. Deuterium is either produced when 2 protons fuse. So it's h squared divided by 2 times the rate of that reaction. Or it's destroyed when a deuterium interacts with a proton. So there's a minus there times the rate of that reaction. So this is the reaction network in the sun. In principle, you have to solve. However, you don't actually have to do that numerically exactly most of the time. The reason is you reach to this network goes in stages. You reach to equilibrium for certain objects very quickly. So for example, you quickly reach to the deuterium equilibrium. That means that the deuterium is no longer changing in the sun. That means the derivative of the concentration of deuterium with respect to time is 0. If you set this derivative to be 0, then you can actually solve the connection between deuterium abundance and hydrogen abundance at equilibrium. And you know what that is. You can calculate deuterium abundance in equilibrium in terms of hydrogen abundance and put that in there. Once you do that, you get this nice reduced set of network equations. Well, lithium and beryllium also reached equilibrium relatively quickly, not as quickly as deuterium, but relatively quickly after deuterium equilibrium. That means you can set those 2 derivatives equal to 0 and calculate beryllium and lithium abundances in terms of other abundances and take them and put them back into this equation, set of equations, then you get this. Now, helium-3 is the thing that reaches the equilibrium the last, but it does. And if you take the helium-3 equilibrium, set this quantity equal to 0, put that everything in there, this is what you get. Well, but you see what this is. Just if you sum them up, that tells you that what's happening in the sun is 4 protons disappearing, 1 alpha particles is being produced. Not surprisingly, that's what the sun does. But the thing here is that, fortunately, in the sun, there is the stage process that you can actually use this. I mean, if you can do this numerically too, of course, and you do it and verify this. Because deuterium reaches equilibrium very quickly. Once you put the values, you'll find that numerically that it reaches equilibrium very quickly. But once you realize that the equilibrium is reached slow in a stage manner for different concentrations, then you can do all that, and then you get this nice expression. That's what I wanted to show you. Sometimes you don't need computers. I'm sorry, this is about I
agree with you, but I won't tell anyone.
Everybody heard it, though.
It's okay. But here, of course, in order to get this original series of equations, you have to do it numerically. All right, so I think this is a good place to stop, and I'll stop here. And I'll continue with that next time. Yeah. Well, you can define a charge conjugation just the same way as you define for the, charge conjugation is an operation. You take the transpose of then you have the definition in your field theory books. You can define them for neutrinos as well. That's important, of course, but the fact that you do not have a mass term, charge term for the neutrinos doesn't mean you cannot apply that particular transformation. That was the genius of Majorana. You're right. I mean, it basically rearranges the terms in the Dirac spinor for the neutrino. That's all it does. But that's what charge transformation, charge conjugation does. I mean, there is no physical meaning like for charged particles, but you can define exactly the same operator.